Okay, looking at the 2015 AB for response number 4. This is the differential equations problem. Fairly easy, simple differential equation 2x minus y. And they ask you to sketch the slope field for these 6 points. And it may not be a bad idea to do a quick little table to help you organize your slopes. So we have these 6 points. We have the ordered pair 0, 2. I'm going to go down the y-axis first, 0, 1, and 0, negative 1. And then we have 1, 2, 1, 1, and 1, negative 1. And I'm simply going to compute the slope at each of those points using the differential equation. So 2 times 0 minus 2 is negative 2. 2 times 0 minus 1 is negative 1. 2 times 0 minus a negative 1 is 1. 2 minus 2 is 0. 2 times 1 minus 1 is 1. 2 minus a negative 1 is 3. And now we'll sketch those slopes at the points. So at 0, 2, I'm going to sketch negative 2. And the way I do that is I visualize a place. I'm definitely going to hit that point. And if I have a slope of negative 2, I'm going to visualize myself connecting it to this point. Now, I'm obviously not going to go all the way down to there, but I want to pretend I'm going to do that and just draw a little piece of a line as if I'm going to connect those. So stick with blue. So there's a negative 2, and then a slope of negative 1. I'm going to connect this point to this point right here. And so negative 1. And then I have a positive 1 right here. So again, I'm going to visualize myself connecting this point at 0, negative 1 to 1, 0. And then I have 1, 2, which has a slope of 0. 1, 1, which has a slope of 1. And then 1, negative 1, which has a slope of 3, which is pretty steep. And at that point, they're almost too steep to really do accurately. So I'm just going to do the best I can. And there is your slope field for part A. Now moving on to part B, they ask you to find the second derivative in terms of x and y. And remember that when you do this derivative is with respect to x. So anything that is not an x must be given the implicit treatment. So derivative of 2x is 2. The derivative of negative y would be negative 1, but you then have to multiply by dy dx. And then they did say to write the equation in terms of x and y. So I will replace that dy dx. That is, I don't know where 2y came from. I'll replace that dy dx with the equation 2x minus y, which I suppose I could change that to 2 minus 2x plus y. No real reason to do that other than it's not that hard to distribute a negative. Then it says determine the concavity of all solution curves in quadrant 2. So in quadrant 2, quad 2, in quadrant 2, your x's are negative and your y's are positive. And so if x is negative and y is positive, then 2 minus 2x plus y. If I plug a negative in for x and a positive in for y, that will always be positive. Therefore, all curves in quadrant 2 would be concave up because the second derivative is greater than 0 for x's negative and y's positive. So there is discussion. I just dropped my pencil. Okay, so there is how you discuss or determine the concavity in quadrant 2. So number C, f is a particular solution with the initial condition f of 2 equals 3. So we have an ordered pair 2, 3 that satisfies one particular solution. Does f have a relative minimum, maximum, or neither, and justify your answer? So in order to have a relative min, max, or neither, the first question is whether x equals 2 is or is not a critical number. So is x equals 2 a critical number for the solution f of x? Because if it's not a critical number, then you don't have a max, min, or neither. You don't have to worry about whether, you don't have to go any further. So first thing I'm going to do is I'm going to evaluate my derivative. at the point x equals 2. Now, since my derivative is a function of x and y, I have to specify that I'm also plugging in 3 for the y's, and my derivative at the point 2, 3 is going to be 2 times 2 minus 3. That is 1. Last time I checked, 1 is not equal to 0. Therefore, 2, 3 is not a critical point. Whoa, a critical point of f of x, and therefore not a relative extrema. If, just for the sake of discussing this, if it did turn out that this was a critical point and it's a candidate for a max or a min, then what you would actually do is use the second derivative, because we have the second derivative in part B, to determine the concavity. If the function's concave up, then you would have a minimum. If the function's concave down, then you would have a maximum. But again, that's only if the first derivative is 0, which it was not. So they kind of bailed us out of further thinking in part C. And then they hit us with a really, really, really weird question in part D. And there are 2 ways to solve this. I'm going to show you both of them. I'm going to show you the more difficult way first. So we are trying to find the values of m and b for which this line, y equals mx plus b, is a solution to the differential equation. Well, first thing I'm going to do is say, well, if y is equal to mx plus b, then that means the derivative of that solution, dy dx, would just be the slope of that line. It would just be m. Well, if dy dx is m, then I could say that 2x minus y is equal to m, because both of those are equal to dy dx. So I can set 2x minus y equal to m. And now I'm going to go even crazier. If I know that y is equal to mx plus b, then I could actually take that mx plus b and substitute it in here, which will give me 2x minus mx plus b is going to equal m. I'm going to distribute that negative, 2x minus 2m. What am I doing? mx? 2x minus mx, not 2x minus 2m. 2x minus mx minus b is equal to m. And then I'm going to do go through a little process similar to how you've probably first learned to solve partial fraction decomposition. I'm going to group my x terms together and factor the x out. And if I factor out an x, that'll leave me with a 2 minus m. And then I still have the minus b. And then over here, I'm going to get really crazy. I want to know how many x's I have on the right side of the equation. And I actually don't have any. There are no x's over there. And so what we can do is on the left side, I have 2 minus m x's. On the right side, I have no x's. So that means 2 minus m must equal 0. And that's pretty easy to solve. M is going to be 2. Then I'm looking at my b term. B is a constant. M is a constant. So the constant on the left must be the same as the constant on the right. That means negative b must equal m. And since I now know that m is 2, I know that negative b is 2 and b is negative 2. And there are your values for m and b, for which mx plus b is a solution to the differential equation. That is a very weird, bizarre, uncomfortable way of thinking about it, but that will work. Now I'm going to show you the second way, which is a little bit of it's quicker, easier to do, but it's trickier to think about. And so the second method would be to think about the fact that if y is equal to mx plus b, then that means that the derivative, I'm going to start with the same process, the derivative would be m, but then I could say that the second derivative would be 0. And so if my second derivative is 0, which the second derivative of a line would be 0, then I can go back to what we found out in part B. We had an equation 2 minus 2x plus y for the second derivative. So from part B, I can now say that, geez, I just forgot the equation. 2 minus 2x plus y, I can now say that 2 minus 2x plus y is equal to 0. And if I solve that for y, I get y is equal to 2x minus 2. Well, if that's what y is equal to, then m is going to equal 2, and b is going to be the constant -2. Therefore, m equals 2, and b equals -2. And that is a very weird, interesting part D, but those are the two methods you can use to solve for the constants m and b.